Hello everyone. Today in this class we are going to start a new chapter number 1, relations and functions. First we will discuss about relations. Relation. A relation are from non-empty set A, from non-empty set A to non-empty set B is defined as a subset of A cross B, that is R is a subset A cross B. Remember, a relation R from non-empty set A to non-empty set B is defined as a subset of A into B, Cartesian product of A and B, that is R subset Cartesian product A and B. If x comma y belongs to R, then we write x is related to y or x r y. X is related to y, read as x is related to y, and if x comma y does not belongs to R, then we write read as x is not related to y. If x comma y, the order where x comma y belongs to R, then we write x r y, read as x is related to R. If the order where x comma y is not belongs to R, then we write x is not related to y. Remember, in a ordered pair x comma y, the first component x is called domain. X is called domain, and second component y is called range. In an ordered pair x comma y, the first component x is called domain and y is called range. Note. Let A and B be two non-empty set, be two non-empty set having m and n elements respectively. Then total number of relations, total number of relations from A to B is 2 to the power mn. 2 to the power mn. Remember, A and B be two non-empty sets. A and B be two non-empty sets having m and n elements respectively. Then total number of relations from A to B is 2 to the power mn. Next, we will discuss types of relations. Types of relations. Number 1, empty relation. Empty relation. Empty relation. A relation are in a set A is called an empty relation. If no element of A is related to any elements of A, that is R is equal to phi proper subset A into B. Remember, what is empty relation? A relation R in a set A is called an empty relation if no element of A is related to any element of A. Remember, a relation R in a set A is called an empty relation if no element of A is related to any element of A. That is R equal to phi proper subset A into A. For example, let A equal to 1, 2, 3, 8, 10, 11 and R be a relation in A given by R equal to ordered pair A comma B such that A minus B equal to 4, then R is an empty relation. Since no element a comma b belongs to A satisfies the property A minus B is equal to 4. Number 2, inversion relation. Number 2, inversion relation. A relation R in a set A is called an inversion relation. If each element of A is related to every element of A, every elements of A, that is R equal to addition product of A into A and A. Inversion. What is inversion relation? A relation R in a set A is called an inversion relation if each element of A is related to every element of A, that is R equal to A into A. For example, let A equal to 2, 3, 4, then R equal to A into A, this equal to A 2, 3, 4 into 2, 3, 4, this equal to 2, 2, 2, 3, 2, 4, 3, 2, 3, 3, 3, 4, 4, 2, 4, 3, 4, 4 is an inversion relation. Is an inversion relation in A. Next, number 3. Number 3, reflexive relation. Reflexive relation. Reflexive relation. A relation R in a set A is called reflexive is called reflexive. If a comma a belongs to R, ordered pair a comma a belongs to R for every a belongs to a belongs to capital A, that is A is related to A for all A belongs to A. Remember, what is reflexive relation? A relation R in a set A is called reflexive if ordered pair a comma a belongs to R for every A belongs to A. That is, A is related to A for all A belongs to A. For example, let A be the set of all real numbers of A be the set of real numbers and relation on it defined as R equal to x comma y such that R equal to ordered pair x comma y such that x plus y belongs to A is reflexive relation. Is a reflexive relation since sum of two real numbers is also a real number. For example, A be a set of real numbers and related on it defined as R equal to ordered by x comma y such that x plus y belongs to A is a reflexive relation because sum of two real numbers is always a real numbers. We take another example. If A is a set of the elements 1, 2, 3 and R is a relation 1, 1, 2, 2 and 3, 3. This relation is called reflexive relation because 1 belongs to A and 1, 1 belongs to R. 2 belongs to A and 2, 2 belongs to R. 3 belongs to A and 3, 3 belongs to R. Therefore, this relation is called reflexive relation. Next, number 4, symmetric relation. Symmetric relation. Symmetry relation. A relation R in a set A is called symmetric. If A comma B ordered pair A comma B belongs to R implies ordered pair B comma A belongs to R. A relation R in a set A is called reflexive if A comma B belongs to R implies B comma A belongs to R. For every A comma B belongs to A. We take an example. A is a set of the elements 1, 2, 3. R is a relation 1, 2, 2, 1, 2, 3, 3, 2, 1, 3, 3, 1. Here 1, 2 belongs to R and 2, 1 also belongs to R. 2, 3 belongs to R, also 3, 2 belongs to R. Therefore, this relation is called symmetry relation. If A, B belongs to R, then B, A belongs to R. Then this relation is called reflexive relation. For every A, B belongs to set A. Number 5, transitive relation. Number 5, transitive relation. A relation R in set A, a relation R in set A is called transitive. If A comma B belongs to R and B comma C belongs to R implies A comma C belongs to R. For every A comma B comma C belongs to set A. Remember, if A comma B comma C belongs to set A relation R is set A. In set A is called transitive. If A comma B belongs to R and B comma C belongs to R implies A comma C belongs to R, where A comma B comma C belongs to set A. For example, A is a set of the elements 1, 2, 3 and the relation 1, 2, 2, 3, 1, 3. Here 1, 2 belongs to R, 1, 2 belongs to R and 2, 3 belongs to R. Also 1, 3 belongs to R. A comma B belongs to R and B comma C belongs to R implies A comma C belongs to R. Therefore, this relation is called transitive relation. If A comma B belongs to R and B comma C belongs to R, that implies A comma C belongs to R. For every A comma B comma C belongs to set A. Next, equivalence relation. Number 6. Equivalence relation. A relation R in a set A is said to be an equivalence relation. If it is reflexive, symmetric, symmetric and transitive. Remember, a relation R in set A is said to be an equivalence relation if it is reflexive, symmetric and transitive. If it is reflexive, symmetric and transitive, then this relation is called equivalence relations. Now, we will discuss exercise 1.1. Now, we will discuss exercise 1.1. Question number 1. Determine whether each of the following relations are reflexive, symmetric and transitive if number 1 relation R in the set A, number 1 relation R in the set A is equal to 1, 2, 3, or 13, 14, defined as R equal to x comma y, R equal to x comma y, such that 3x minus y equal to 0, such that 3x minus y. Determine the relation reflexive, symmetric and transitive. R equal to A equal to 1, 2, 3, 13, 14, and R is equal to ordered by x comma y such that 3x minus y equal to 0. Solutions. Here A is equal to 1, 2, 3, 13, 14. R is equal to ordered pair x comma y such that 3x minus y is equal to 0. Therefore, this equal to here 3x minus y equal to 0. Therefore, we can write 3x minus y equal to 0, y is equal to 3x. If putting x equal to 1, then we have y equal to 3. If putting x equal to 1, then we have y equal to 3. Therefore, the first order pair is 1, 3. Next, if putting x equal to 2, then we have y equal to 6. Putting x equal to 3, then we have y equal to 9. If putting x equal to 4, then we have y equal to 12. If putting x equal to 5, then we have y equal to 15. If putting x equal to 5, then we have y equal to 15. Here, 15 is not belongs to set A. 15 is not belongs to the set A. And therefore, the relations are 1, 3, 2, 3, 3, 6, 4, 12. Now, 1 belongs to A. Now, 1 is an element of the set A, but 1, 1 is not belongs to R. Now, 1 is the element of set A, 1 belongs to A, that means 1 is the element of the set A, but 1, 1, the ordered pair 1, 1 is not belongs to A. We know that if A is the element of set A, if A comma A belongs to R, then the relation is called reflexive relation. Here 1 is belongs to set A, but 1, 1 does not belongs to R. So R is not reflexive relation. R is not reflexive relation. Next, 1, 3, we know that if A comma B belongs to R, then B comma A belongs to R, then this relation is called symmetry relation, where A comma B belongs to set A. Yes, A relation R is said to be symmetric relation if A comma B belongs to R, that implies B comma A belongs to R, where A comma B belongs to set A. Here 1, 3 belongs to R, 1 comma 3 belongs to R, but 3 comma 1 is not belongs to R, but 3 comma 1 is not belongs to R. Here 1 comma 3 belongs to R, but 3 comma 1 is not belongs to R. Therefore, R is not symmetric relation. So R is not symmetric relation. So R is not symmetric relation. Next, we know that A comma B comma C belongs to the set A. We know that A comma B comma C belongs to set A. If A comma B belongs to R and B comma C belongs to R, this implies A comma C belongs to R, then this relation is called transitive relation. If A comma B comma C belongs to set A, if A comma B belongs to R and B comma C belongs to R, that implies A comma C belongs to R, then this relation is called transitive relation. Here 1 comma 3 belongs to R. Here 1 comma 3 belongs to R and 3 comma 9 belongs to R. But 1 comma 9 is not belongs to relation R. Therefore R is not transitive relation. R is not transitive because 1 comma 3 belongs to R and 3 comma 9 belongs to R, but 1 comma 9 is not belongs to relation R. Thus R is neither reflexive, R is neither reflexive nor symmetric nor transitive. R is not reflexive nor symmetric nor transitive. Next, Roman number 2. Relation R in the set N of natural number defined as R equal to ordered pair x comma y such that y equal to x plus 5 and x less than 4. Roman number 2. Determine the reflexive, symmetric and transitive. R in the set N natural number defined as R equal to ordered pair x comma y such that y equal to x plus 5 and x less than 4. Here R equal to x ordered pair x comma y such that y equal to x plus 5 and x less than 4. Then we put x equal 1, 2, 3. Then we have putting x equal to 1, then we have y equal to 6. Putting x equal to 2, then we have y equal to 7. Putting x equal to 3, then we have y equal to 8. This is the relation 1, 6, 2, 7, 3, 8. A equal to 1, 2, 3. Now 1 belongs to set A. 1 belongs to set A. 1 is belongs to set A, but 1, 1 is not belongs to relation R. Therefore, this relation is not reflexive relation. Therefore, so R is not reflexive relation. R is not reflexive because 1 belongs to set A, but 1 comma 1 is does not belongs to set relation R. 1 comma 6 belongs to R, but 6 comma 1 does not belongs to R. 6 comma 1 does not belongs to R. 1 comma 6 belongs to R, but 6 comma 1 does not belongs to R. Therefore, R is not symmetric relation. So, R is not symmetric relation. Symmetric relation. R is not symmetric relation. If in R A comma B belongs to R, but there is no ordered pairs, there is no ordered pair B comma C, ordered pair B comma C belongs to R. There is no ordered pair B comma C belongs to R. So R is not transitive relation. Transitive relation. Here 1 comma C belongs to R, but there is no ordered pair. Here A comma B belongs to R, but there is no ordered pair B comma C belongs to R. So R is not transitive relation. So thus R is neither reflexive, not transitive, not symmetric, not transitive. This is the record answer. Therefore, R is not neither reflexive, nor symmetric, nor transitive. Next, we will discuss question number 3. Question number 3. Question number 3. Check whether the relation R defined in the set A is equal to 1, 2, 3, 4, 5, 6 as R is equal to ordered pair A comma B such that B is equal to A plus 1 is reflexive, symmetric or transitive. Given the set A is equal to 1, 2, 3, 4, 5, 6 and R is equal to ordered pair A comma B such that B equal to A plus 1 is it is reflexive, symmetric or transitive. Solutions. Here A is equal to 1, 2, 3, 4, 5, 6 and R is equal to ordered pair A comma B such that B equal to A plus 1. Therefore, this equal to, putting A equal to 1, then we have B equal to 2. Putting A equal to 2, then we have B equal to 3. Putting A equal to 3, then we have B equal to 4. Putting A equal to 4, then we have B equal to 5. Putting A equal to 5, then we have B equal to 6. Now 1, 2, 3, 4, 5, 6 belongs to set A, but 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6 does not belongs to set A. Since 1, 2, 3, 4, 5, 6 belongs to set A, but 1, 1, 2, 3, 4, 4, 5, 6, 6 does not belongs to relation R. So R is not reflexive relation. Reflexive relation. Now 1, 2 belongs to R. 1 comma 2 belongs to R, but 2 comma 1 does not belongs to R. But 2 comma 1 does not belongs to. Well, 2 comma 1 is not belongs to R. So R is not transitive. R is not transitive. Sorry, symmetric. 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 If A comma B belongs to R, but B comma A does not belongs to R, then R is called, R is not symmetric. Then R is not symmetric relation. Symmetric relation. Next, 3 comma 4. 3 comma 4 belongs to R. 4 comma 5 belongs to R, but 3 comma 5 is not belongs to R. Or 1 comma 2 belongs to R, and 2 comma 3 belongs to R, but 1 comma 3 is not belongs to R. 1 comma 2 belongs to R, and 2 comma 3 belongs to R, but 1 comma 3 is not belongs to R. Therefore R is not transitive. Therefore R is not transitive relation. R is not transitive relation. Thus R is neither reflexive nor symmetric nor transitive. This is the required answer. Next we will discuss question number 6. Now we will discuss question number 6. Question number 6. So that the relation R in the set 1 comma 2 comma 3 R is equal to 1 comma 2 2 comma 3 2 comma 1 is symmetric but neither reflexive nor transitive. Given the set 1 comma 2 comma 3 and a relation 1 comma 2 to the outer pair 1 comma 2 and 2 comma 1, it is reflexive but not, so that it is reflexive but not symmetric nor transitive relations. Here A equal to 1 comma 2 comma 3 and R is equal to 1 comma 2 2 comma 1. Now it is symmetric but neither reflexive nor transitive. Now 1 belongs to A, but 1 comma 1 is not belongs to R. Therefore 1 is the element of the set A, but 1 comma 1 is not belongs to the relation R. So R is not reflexive. R is not reflexive relation. R is not reflexive relation. 1 comma 2 belongs to R and 2 comma 1 belongs to R. Therefore R is symmetric relation. We know that if A comma belongs to R, A comma B belongs to R, and B comma A belongs to R, then R is called this relation is called symmetric relation, where A comma B belongs to the set A. So R is symmetric. R is symmetric relation. R is symmetric relation. Next 1 comma 2 belongs to R and 2 comma 1 belongs to R. 2 comma 1 belongs to R, but 1 comma 1 is not belongs to R. Therefore this relation is not transitive. So this relation, therefore R is not transitive relation. R is not transitive relation. So R is a symmetric. Thus we can say that thus R is symmetric, but neither reflexive, nor transitive. This is the record answer. Next, we'll discuss question number 9. Question number 9. So that each of the relation R in the set A equal to x belongs to Z, where 0 less than equal x less than equal 12 given by R equal to ordered pair A comma B such that modulus A minus B is a multiple of 4. Next one, number 2, R is a relation. It is equal to ordered pair A comma B such that A equal to B is a equivalent relation. Find a set of all elements related to one in each case. Here A is equal to x belongs to Z. Z means integer. X belongs to Z such that 0 less than equal x less than equal 12. This is equal to 0, 1, 2, 3 to 12. Roman number 1, R equal to ordered pair A comma B such that A minus B modulus A minus B is a multiple of 4. Ordered pair A comma B such that modulus A minus B is a multiple of 4. This equal to 0, 0, 0, 4, because 0 minus 0 modulus 0 minus 0 is equal to 0. 0 is a multiple of 4. Modulus 0 minus 4 is equal to 4. 4 is a multiple of 4. Next 0, 8, 0, 12, 1, 1, 1, 5, 1, 9, 2, 2, 6, 2, 10, 3, 3, 7, 3, 11, 4, 4, 8, 4, 12, 5, 5, 9, 6, 6, 10, 7, 7, 11, 8, 8, 9, 8, 12, 8, 12, 9, 9, 10, 10, 11, 11, 12, 12. 0, 0, because modulus 0 minus 0 is equal to 0. 0 is a multiples of 4. Ordered pair 0, 4, because modulus 0 minus 4. Modulus 0 minus 4 is equal to 4. 4 is a multiples of 4. 0, 8. Modulus 0, 8 is equal to 8, which is multiples of 4. 0, 12. 0 minus 12 is equal to 12, which is multiples of 4. 12 minus 12, modulus 0, which is multiples of 4. Here, now 0, 1, 2, 12 belongs to A, set A, and then 0, 0, 1, 1, 12, 12, which is belongs to the relation R. Therefore, R is a reflexive relation. So R is a reflexive relation. Therefore R is a reflexive relation. Next 1,5 belongs to R, then 5,1 belongs to R. 1,5 modulus 1 minus 5 is equal to 4. 4 is a multiple of 4. Modulus 5 minus 1 is equal to 4. 4 is a multiple of 4. Therefore this relation is symmetric. 1,5 belongs to R, then 5,1 belongs to R. Then because modulus 5 minus 1 is equal to modulus 1 minus 5. So R is symmetric. R is symmetric relation. R is symmetric relation. Next 2,6 belongs to R and 6,10 belongs to R. Then 2,10 belongs to R. Modulus 2 minus 6 is equal to 4. 4 is a multiple of 4. Therefore 2,6 belongs to R. Modulus 6 minus 10 is equal to 4. 4 is a multiple of 4. Therefore this belongs to R. And 2 minus 10, modulus 2 minus 10 is equal to 8, which is multiples of 4. Therefore this ordered pair is belongs to the relation R. Therefore this relation is called transitive relation. So R is transitive relation. Transitive relation. Thus R is an equivalence relation. The set of elements related to 1 is 1,5,9. Next, Roman number 2. Next, Roman number 2. R is equal to ordered pair A comma B such that A is equal to B. This equal to 0 comma 0 because 0 equal to 0, 1 comma 1 because 1 is equal to 1, 2 comma 2 to 12 comma 12. Now 0 comma 1 comma 2 comma 3 to belongs to A. Then 0 comma 0, 1 comma 1 to 12 comma 12, 12 comma 12, which is belongs to the relation R. Therefore R is reflexive relation. Therefore R is a reflexive relation. Therefore R is a reflexive relation. Reflexive relation. 2 comma 2 belongs to R, then 2 comma 2 belongs to R. So R is symmetric relation. So R is symmetric relation. R is symmetric relation. 5,5 belongs to R and 5,5 belongs to R, then 5,5 belongs to R. A comma B, here A equal to 5, B equal to 5. A comma B belongs to R. B comma C, here B equal to 5, C equal to 5. B comma C belongs to R, then A comma C belongs to R. Therefore R is transitive relation. R is transitive relation. R is transitive relation. Thus, R is an equivalent relation. Thus, R is an equivalence relation. Equivalence relation. The set of elements related to one is one. This is the required answer. Thank you.